हेलो फ्रेंड्स। तो अभी तक हमने सेमीकंडक्टर्स के बारे में पढ़ा। इंट्रिंसिक सेमीकंडक्टर एंड एक्सट्रिंसिक सेमीकंडक्टर। एक्सट्रिंसिक सेमीकंडक्टर आर आल्सो ऑफ टू टाइप्स, पी टाइप एंड एन टाइप। पी टाइप सेमीकंडक्टर्स वो होते हैं जिसमें जो इम्प्योरिटी हम ऐड कर रहे हैं वो ग्रुप 3 एलिमेंट्स के हों। अगर ग्रुप 5 के एलिमेंट्स हम ऐड कर रहे हैं एज एन इम्प्योरिटी तो वो एन टाइप बनेगा। ओके, so today we will discuss about what is the effect of extrinsic semiconductor. I mean, what is the effect of why we need extrinsic semiconductor when we have pure semiconductors, and what is the effect of it on temperature and any environmental external source. So first of all, what is energy band gap of extrinsic semiconductor? We know energy band gap is the gap of energy between valence band and conduction band. It is 1.1 for silicon, pure silicon atom. It is 1.1, but when we add doping to it, the energy gap reduced by the value 0.05 electron volt. You can see how much it is reduced. 1.1 to 0.05. That means very less energy gap is now very less energy is needed to make the electron jump from valence band to conduction band. Okay, now our next topic is now what I'm telling you, I'm here. So as we know, energy band gap of silicon is 1.1, but it is reduced by the value 0.05 electron volt. That means the energy gap is in electron volt and the gap is reduced. Okay, uh, why it reduces? It reduces because it is an intrinsic property of doping. It is due to doping. If we add p types or n type impurity to a pure semiconductor, then it becomes extrinsic semiconductor, and extrinsic semiconductor is different from intrinsic. Extrinsic energy gap is very small. In case of extrinsic semiconductor, energy gap is very small. Band gap energy band gap now becomes this 1.1 to 0.05 electron volt. Energy gap also depends on temperature. This gap depends upon temperature, means while increasing temperature the band decreases. Okay, how it decreases? There is a formula that energy gap at temperature, at any temperature T, is equals to energy gap at zero temperature minus 3.6 into 10 to power minus 4 T. Suppose we have temperature 300. 300 we know normal our room temperature. So at energy gap 300, 1.21 minus energy gap at zero temperature, what is 1.21 minus 3.6 into 10 to the power minus 4 into temperature at what temperature? At 300 temperature, it comes out to be 1.1 electron volt, and simply energy gap is 1.1 electron volt. Okay, similarly from energy gap from for germanium के लिए भी निकाला हुआ है, देखो energy gap at any temperature. Suppose we are taking at 300. At 300 temperature, energy gap at zero temperature, at zero energy gap for energy gap at zero temperature for germanium is 0.785. Okay, so minus 2.33 into 10 to power minus 4 into temperature, then it comes out to be 0.72 electron volt. That's why energy gap is 0.72 at room temperature. For silicon it is 1.1 electron volt, for germanium it is 0.72. We can say that the energy gap is less for germanium as compared to silicon. So we can prefer germanium if we need a very initiant or very fast response, we can use germanium. But in most of the cases, silicon is preferred because silicon is very abundant. I mean, in nature, we have more silicon than germanium. It is very abundant. There is abundance of silicon. Effect of temperature on extrinsic semiconductor. What is the effect of temperature on semiconductor? Okay. As temperature increases for extrinsic semiconductor, all impurity atom converted into ions at low temperature. This situation partial. Below 200 degree Kelvin, the charge energies are only sufficient to partially ionize the impurity atom. At the usual, the ambient temperature, all the donors and acceptor will be ionized. The density of charges available for conduction is constant and essentially equal to the density of impurity atom. Above 400, the density of thermal generated pair begin to increase in exponential fashion, and at temperature where electron and hole deficiency approach equally, the conduction process becomes intrinsic. What is it telling about here? It is telling about this graph. This graph is at between temperature and between energy gaps. Now it says what it says. It simply says that if we increase the temperature, the conductivity increases. Okay, simply says, but in different manner. To ensure that we have current only at majority carriers, we must operate material in the range below the intrinsic conduction temperature. Thus, germanium devices are limited to a maximum temperature of 85 to 100 degrees Celsius and silicon devices up to 200 degrees Celsius. That's why at high temperature we prefer silicon because germanium maximum temperature limit is 100 degrees Celsius and silicon's maximum limit is 200 degrees Celsius because at that temperature they behave like a normal semiconductor, they behave like intrinsic semiconductor. What is telling here? As the temperature increases, extrinsic semiconductor, all impurity atom converted into ions. They becomes like ion, they start vibrating. But at low temperature, the situation is partial. Means at the low temperature, some are ionized, but some are not ionized. They donate in conduction. Below 0 to 100 degree Kelvin, charge can near only sufficient to partially ionize the impurity atom. As the usual ambient temperature, all the donor acceptor will be ionized. The density of charge density will always remain same. At either temperature, density will remain same. Okay. Electrical neutral equation is given for extrinsic semiconductor. Neutral is I am telling about density is same. So if number of negative charge, what is the number of negative charge? That is n number of electrons plus n is the density of electrons, p is the number of holes plus n, d is the number of positive charge. What is telling about, as I said, you are extrinsic semiconductor. If we add, suppose we have n type semiconductor, what is here? N type, extra electron is there, that means number of acceptor atoms, number of donor atoms which have electrons excess amount, that the n type have excess electrons, that means they are donor. The number of protons, I mean protons in holes, number of holes, okay, number of holes किसके बराबर होंगे? नंबर ऑफ होल्स प्लस नंबर ऑफ जितने हम इम्प्योरिटी एटम कर रहे हैं, इम्प्योरिटी एटम ऐड कर रहे हैं, जितनी उसकी डोनेट करने की क्या, इसको आप ऐसे समझ सकते हो इन इजी वे the most easy way is that we know number of uh, n is number of electrons. Number of electrons, extra electrons कितने होंगे जितने हमारे पास नंबर ऑफ एक्सेप्टर एटम होंगे Na होंगे, ठीक है, नंबर ऑफ एक्सेप्टर एटम। और P कितने होंगे जितने हमारे पास मतलब होल्स कितने बनेंगे, एक्चुअली यहाँ पे डोनर आएगा। नंबर ऑफ इलेक्ट्रॉन्स जितनी उसके अंदर इलेक्ट्रॉन्स एक्स्ट्रा होंगे उतने कितने होंगे, डोनर होंगे। क्योंकि अगर हम जैसे मैंने पढ़ा कि डोनर क्या होगा, डोनर वही होगा जिसके पास ज्यादा होंगे। तो ज्यादा किसके पास है, एन के पास है, तो नंबर ऑफ इलेक्ट्रॉन्स किसके बराबर होंगे, एन ऑफ डी के बराबर होंगे, ठीक है। और प्रोटॉन होल्स किसके बराबर होंगे, एन ऑफ ए के बराबर होंगे। तो एडिंग बोथ द इक्वेशन एन प्लस पी कम्स आउट टू बी एन ए प्लस एन डी, एंड n plus p equals to na plus nd if we either interchange or we can simply have that change.